Good evening, everyone. Am I audible?
Yes, ma'am. Good evening, ma'am.
Yes, ma'am. Good evening.
Okay.
Yes, ma'am.
So, this session will start by a question that my screen is visible, right?
Yes, ma'am.
Yeah. So, just take 5 minutes to observe these two graphs, A and B, and try to answer that that the number of minimum color we required to color both of the graphs. Okay. And answer in the chat box. Answer separately how many colors for A and how many colors for B. Okay, fine. So let us discuss this type of question. So first thing is that how you will attack such type of question. Okay. So first, what you will observe that which vertex is connected to most maximum number of vertices. For example, in this graph, this vertex number 1 is connected to almost every other vertex, right? So it first assign a color to this vertex. So let us suppose that I assign a red color to this vertex. So suppose I am assigning red color to this vertex. Now I'll move to some another vertex. Suppose I am moving this vertex which is named as 2. Okay. So now this 2 vertex is adjacent to this 1 vertex. So I cannot use this red color for coloring this vertex number 2. Okay. Yeah, right. So what I'll do, I'll choose another color, and suppose I'll choose blue color, and I'll color this vertex using the blue color. Now I'll move. Now I'll move to next vertex. Now this vertex 3 is also associated, also adjacent to this vertex 1 and this vertex 2. So I cannot use the red and blue color. So again, I have to go for some another color. So suppose I'll assign this vertex some another color. Okay. Now I'll move to next vertex. So next vertex is 4. So now this 4 vertex is adjacent to this 3 vertex and adjacent to 1 vertex. So I cannot use the red color and this color, but I can use the blue color. So I'll color this vertex number 4 as using the blue color. Okay. Similarly, I'll move to the next vertex, which is again 5. So again 5 is adjacent to 1 and 4. So I cannot use these both color. I'll use some other color. Let's suppose this is my other color. Okay. Similarly, I'll again move to some other vertex. I'll associate it to be blue color. Then again, I'll associate this to be this color. And to the next vertex, I'll again associate the blue color. To the next vertex, I'll associate this color. And at the next, now what happened to the vertex 10? This 10 vertex is adjacent to 9, 1, and 2. And I mean, I cannot use this color, red color, and blue color. So I have to choose some another color for this vertex 10. So that's why for coloring this graph, I need 4 color. And using the similar approach, you can find out that for coloring this graph, I need just 3 colors. So that's the difference between these two graphs. Okay. So in last lecture, we just say that, okay, 3 color will be sufficient, but it is not always the case. If we have even number of vertices, then we need 4 colors. And if we have odd number of vertices, then we need 3 colors. So this is one important example of regarding the coloring of a graph. Highly approach and what should be your answer? Okay, fine. Then we
Ma'am,
move to
in general, for any even number.
yeah, because what happened in even number, you will come across this situation that you're surrounded by 3 vertices which contain different colors. But in odd, what happened here, you will get, I guess, suppose blue color. Here you will get blue color. I mean, in the both side of 10 you have different color, right? But in the
Yeah,
case of odd vertices, you will surrounded by the vertices which will have same color, right?
yeah, but in the case, in this case, in the way they are connected now,
Yeah,
if they are
yeah, yeah.
connected in
That
different
is that
order,
type of
then it
graph.
might be different.
Yeah, obviously. The if we have some other situations, then obviously it is different. But that should be your approach. That observing how what are the minimum number of colors required for coloring. Okay, as a one important example. Okay, so now we go for next topic, which is depth or such. Okay. So again, this is a process for finding the reachability path or finding the tree in any graph. So I'll explain this process in a minute. Okay. Suppose we have this graph. This is your G, and we have vertices A, B, C, D, E, F, G, H. Okay. So in the DFS, what we will do? So we will move along the path. I mean, suppose, okay, okay. So in DFS, we manage stack data. Uh, what can you say? I mean, we in place of queue, we'll use stacks to collect our associated vertices. Stack means that stack will use last in, first out system. I mean, whichever vertex we put at the last, that vertex will process at first. So that's the meaning of stack. And in queue we have this form that first in, first out. Okay. So DFS for applying DFS, let us suppose I'll start this vertex B. So initially all the vertices are not visited. So that's why I'll taking all the entries to be false because none of them is visited till yet. So now if I'll select my B, so as in the BFS process, I will mark it to be true and I will collect into I'll collect this vertex B into my stack. But what will DFS do? DFS just go through the neighbors. I mean, B has two neighbors, A and C, so I can select any one of them. Suppose I'll select. So what is happening here? That I'm marking B, and now I'll leave B and I'll go to other vertex, other neighbor of B. So that means I'll suspend B, and now I'll explore the other vertex, which is a neighbor of B. Suppose A. You can choose any one of them. I mean, you can choose A or C, any one of them, and whatever vertex we are suspended, we'll add that vertex to into our stack. Suppose I am suspending B, so I'll add that vertex into my stack. Okay. In the next step, what I'll do, so I'll again suspend A, because I have a way to move forward from A, right? I can go to E, I can go to D, I can go to C, any one of them I can move, right? So whenever we have a way to go further, we'll go taking whatever vertex we want. In BFS, what we'll do, we'll explore each vertex one by one. For example, in if I'll run my BFS over this graph, what I'll do, first I will explore B, then I'll explore all the neighbors of B, and then I'll move further. That means I'll move level by level in BFS. But in DFS, what we'll do, we'll just pick a vertex, explore its one of the neighbor, and then go further. If there is a way, we'll go further. If not, we'll come back. Okay. So now what I'll do, I'll suspend my A again. So whenever I'm suspending a vertex, I will add it to my stack. And now I will explore any neighbor of A. Suppose I'll exploring C. Okay. So now, so I started from B, I moved to A, then I'm going at C. So, but there is another way. I mean, we can move further away from C, right? I can go to D and I can go to E. So there is a possible path to the next unvisited vertex, right? So again, here A is visited. So I'll just mark it to be true. Okay. So now again, what I'll do, I'll suspend my C and I'll explore one of the neighbor of a C. Suppose I'll explore the D. Okay. So explore D. So whenever I suspend a vertex, I will add it to my stack. Okay. Now again, from D, I have a way to move further, right? From D, I can go to E. Whenever, B, A, and C are already has been visited. So we don't want to go back. We want to go further. Okay. So there is a way from moving away from D. So I mean, there is a vertex which is unvisited, and we have an edge between the vertex D and E. So what I'll do, again, I will suspend my D. So I'll suspend my vertex D, and now I want to explore E. So whenever I suspend a vertex, I will add it to my stack. Okay. Now similarly, there is a way from moving away from E. So again, I'll suspend E and explore its other vertex called F. Okay, so whenever I suspend, I'll add it to my stack, and also I'll mark it to be true that it is visited. Okay. Also, I have to mark D to be true. Okay. Now in the next step, I'll again suspend
And
F.
C also,
Yeah.
visited.
Correct. Yeah, already visited, right? So now again I'll suspend my F, because there is a way from going away from F. So I'll suspend F and explore any one of its neighbor. So there are two neighbors of F, H and G. So let us assume we'll exploring H. Okay. So again, there is a vertex which is connected to H and which is not visited. So that means we can always suspend our H also. So F, I'll add it to the stack. Now again, I'll suspend my H and explore G. Okay. So also H is also added to the stack. Okay. Now, when we reach to G, there is no other unvisited vertex that we can go. So that means we should, now we will stop our process here, and now we will backtrack our path. Okay. Suppose there is this vertex. Suppose our graph will look like, suppose these are two other vertex, I and G. Okay. Then what happened? I reach at G, but there is no edge which is connecting to G to H or J. So that means I cannot move further from G. Okay. So what I will do, I'll backtrack my path to that vertex which is connected to I or J. Okay. So if I'll backtrack my path, what will be the case? So I am doing backtracking. So I'll backtrack from G to H. So whenever I backtrack any vertex, what I'll do, I will remove that vertex from my stack. Okay. So I'm backtracking to H. So I'll remove H from my stack. Again, I'll backtrack. How we move? We go. Yeah. So again, we'll backtrack. So we reach at F. So I'll backtrack from H to F, and I'll remove F from my stack. Again, I will backtrack to E, because there is no edge from F to I or J. So that's why we have to backtrack, so that we can cover these two vertices also, right? Okay. So again, we are backtracking from F to E. So I'll remove E from my stack. Now again, I'll backtrack from E to which vertex? E to A, right? Okay. And I will remove my A from my stack. Okay. But now what happened? From A, I have an edge which is connected to I, which is an unvisited vertex, right?
Uh,
These B and
ma'am,
H are also visited.
initially we suspended D and explored E. So when we are
Yeah, yeah.
returning from E, should not we go for the D? What
Oh,
we
yeah.
did
Sorry.
in D?
We there is D and C between them, right? I'll forgot what is there. Okay, so again I'll backtrack to D. Ultimately, we'll reach at A, right? From D, I will go to C, and then from C,
One more query here. Like when we are
yeah,
doing that, when we are adding the unvisited vertexes to the stack, is
yeah,
it adding just one neighbor that we are going to explore further,
yeah,
or
yeah,
just
yeah. Just one
oh,
neighbor,
okay,
whatever you want to explore. I mean, whatever vertex will suspend and go to the another level, that suspended vertex should be added to your stack. That's the thing, right?
just a single, not all the neighbors.
Yeah, just a single. In DFS, in BFS, what we'll do, we'll add all the neighbors. But in DFS, we go one by one.
Okay.
That's the thing. Okay. So here I backtrack till A. Now there is a path from A to I. So what I'll do now, I will again suspend my A, and I'll explore I. Right? Okay. So whenever I suspend A, so I'll add it to my stack, and now I'll set this entry to be true, since I is now visiting. Okay, visited. And again, there is a vertex J which is unvisited, and there is an edge between I to J. So that means I can go further. So that's why again I'll suspend my I, and I'll explore J. Right. So whenever I suspend a vertex, I will add it into set. Now what happened from J? We cannot go further, right? So again, I have to do backtracking so that my all suspended vertex have been removed, right? So that means DFS will stop whenever when your stack get empty, right? As like in BFS, we will stop BFS when we have an empty queue. Similarly, when we'll stop our DFS process whenever we have an empty stack. Okay. So now I'll backtrack again. So I'll backtrack my I from J, right? Now I'll remove this I, and similar thing can be done for A, backtrack A and remove A, and similarly backtrack B, and I'll remove my B. And what happened? All the vertices are visited, and we have completed our BFS process. So that's the main part of BFS, that how BFS work. Actually, BFS work, I mean, randomly. You can choose first, you will start from B, go to A, go to C, or you can go to C first and then go to another vertex. It doesn't matter, right? Okay. So you got what is the BFS? Yes.
Ma'am, when we are backtracking from, say, from H to G to F to E, and
Yeah.
then since we went through the D and C route, so we will backtrack to D and C and then go back to A, right? We will not go from E to
We will follow the same path in which path we have moved forward, right?
Oh,
That's the
okay.
point. Yeah, I missed some of the vertices. but that's the rough process of DFS. You guys try to work by your own so that you will remember how we should go forward and come backward. Okay.
Okay.
Just do it by once. It's easy because whatever you're doing, so we'll select a vertex, go to its favorite neighbors, then go to another neighbor, then go to another neighbor till we'll process uh, till then whenever we have a situation that we cannot go to some new vertex, right? Then whenever this situation will happen, we will just backtrack our path and again try to find out a vertex which is connected to that new vertex, and again we'll suspend that vertex and explore new vertices. So that's the DFS main process. Okay.
Okay.
Yeah.
Ma'am,
Yes.
you said stack is working like last in first out.
Yeah, last in first out.
Can you explain here how it is works?
Yeah, because what happened first in the first at the first what we can say, B is our first selected vertex, right? So uh, B come into picture before A. But what will happen? I will first erase my A, or I will first leave. I will first take out my A before I take out my B. So that's thing. That A come at last, right? B come at first. But what happened in the process? I will take A before I'll take B. I'll backtrack A before I backtrack B. So that's the meaning of last in first out, right? In a queue, what happened? First in first out. If you are in a queue to buy a ticket or something, then the person who stands before you will get ticket first, right? In the stack, what will happen? Stack at the last person will get the ticket first. That's the stack. Last in first out.
Okay.
Yeah. Okay.
We can think of a queue as a pipe, right?
Yeah. You can think, yeah, because in that case also first in, first out.
Right.
So this is your DFS, sorry. Now I'll go for trees and all, tree cycles. Yeah. So you guys know what do we mean by cycle, right? Cycle is a path in which starting and endpoint are same. And in a path, we are not allowed to visit a vertex twice, right? Or we are not allowed to visit a edge twice because there is no multi-edge and all concept. So that's why. Okay. So you guys also know what do you mean by a connected graph, right? So connected graph is basically a graph in which there is a path between any two vertices. You take any vertex from anywhere of the graph, you can find a path so that you can move to other vertex. For example, this graph. Okay, so this graph is connected graph because if you suppose I'll take C and I'll take E, so then there is a natural way from moving C to E, right? There is a path between C to E. So that means there is a path between any two vertices in a graph. That graph is called connected graph. So a tree is basically an acyclic connected graph. What do you mean by acyclic? Acyclic means that graph does not have any cycle. That graph does not contain any cycle. For example, the basic example of tree is such like this. Right? This is a tree. Since it is connected, because you can easily find a path between any two vertices, and there is no cycle, right? There is no cycle in this graph. You cannot find a cycle. So this is an acyclic connected graph. So an acyclic connected graph is called a tree. Okay. Now, what do you mean by a degree of an vertex? Vertex in a graph G. So we have two types of graph. First is directed graph and another one is undirected graph. So in undirected graph, The degree of vertices means just basically the number of edges associated to vertex V. That how many edges are associated to a vertex is known as a degree of vertex. For example, in this tree, if you assume this is your vertex A, then how many edges are associated to A? 3, right? This one, and this one. So that's why degree of A is 3. And this is an undirected graph, right? I am not giving any direction to any edge. So in an undirected graph, a degree of a vertex is basically the number of edges associated to that vertex. Okay. And in directed graph, we have two types of degree. First is called in degree, and another one is out degree. So in degree is again the number of edges which are coming at V, the number of edges which are coming at V, and out degree is the number of edges which are moving away from V. You can assume like that. Okay. For example, if I have this graph, so I have this graph, and this is a two-sided edge. This is also a two-sided edge, and this is my vertex A. Then the in degree of A is how many edges are reaching at A. So there are 3 edges which are reaching at A, right? The graph is clear, right? These 3 edges are going at A. So in degree is 3. And what is the out degree of A?
1.
So out degree of A, what are the edges moving away from me? So basically there is 1 edge, 2 edge moving. Sorry, what? 2. Yeah. So this is a basic concept of degree. So in an undirected graph, degree is just number of edges associated to a vertex. In a directed graph, we have 2 type of degree, in degree and out degree. Okay. Fine. So now suppose I have a graph G, which has some vertex at V and some edge at E, right? Okay. Suppose we have n vertices. The cardinality of vertex set is n, right? So then the first question rises that what is the maximum number of edges, possible in a graph, right? Okay. So what should be the answer?
N minus 1.
N of n minus 1 by 2.
N minus
Yeah. So what is the maximum possible number of edges in a graph is basically n into n minus 1 by 2. Because what happened, we can form an edge from starting a vertex V to any for a vertex, for a first vertex. Suppose this is my first vertex of a graph. So there are n choices, n minus 1 choices, or n minus 1 edges can be formed to the other vertices, right? If I move to the second vertex, then I have n minus 2 edges which we can make for the another vertex, right? So in the similar way, in the similar fashion, if I'll move, what I will get? I'll get n into n minus 1 by 2. Now, actually, this is a formula for actually number of subsets, number of cardinality 2 subsets of n set of cardinality n. You can basically, you can say, what happened? What is an edge? So an edge is basically a pair of 2 vertices, right? And we have n vertices. So for this pair, I have n choices. For this place, I have n choices. And for this place, I have n minus 1 choices because I am not allowing the loop. So that means I have total number of n into n minus 1 choices, right? But what happened in an undirected graph, and I am taking this situation in undirected graph, okay? Yeah.
Ma'am, number of subsets is 2 power n, right?
Ma'am,
No, actually number of subsets which has, okay, just forget this thing, okay?
ma'am, in directed graph, it is n into n minus 1, no?
In directed graph, we actually won't talk about how many number of edges are possible because there is direction constraint. Actually, number of edges are actually same, but just directions are different. So we don't bother about that thing. So what I was explaining, that NH is basically a pair of vertex. So for this place, I have n choices. For this place, I have n minus 1 choices. But what happened? I'm saying that U, V and VU, this both pair will give me the same edge, right? Same edge. So that means I'm counting twice. So that's why I have to divide by 2. So that this is the number of edges. Or I can say this is the maximum possible number of edges. Okay. So you got this thing, right? What is the maximum possible number of edges in any graph with n vertices is basically n into n minus 1 by 2. Now, what is the minimum number of edges possible? What is the possible minimum number of edges?
0.
What is the answer?
N.
If I consider it to be a
0.
connected graph, then that's n minus 1.
No, I am not considering connected anything. I'm saying this basically an undirected graph which has n vertices. Then what is the possible number of, what is the possible number of minimum edges?
0, ma'am, if it is not
Zero.
connected.
1, ma'am.
Actually, it is 0 because it is possible now there does not exist any edge. That itself form a graph, right? Because E is basically a subset of V cross V, and E could be phi. Phi is also a subset of V cross V, right? The how we define the graph, that the number of edges, the edge set is basically a subset of V cross V, right? And an edge set could be phi, and phi is also a subset of V cross V. So that means the possible minimum number of edges in n vertex graph is 0. Okay. So that's the one thing. Now we come across the main theorem or main lemma, which is known as handshaking lemma. Okay, so handshaking lemma says that if you take sum of the degrees, so again suppose I have n vertices v1, v2, and so on vn, then the sum of the degrees of all n vertices, that degree of v1 plus degree of v2 plus and so on plus degree of vn, this is actually equal to 2 times the cardinality of E. That means 2 times the number of edges. This is known as the handshaking lemma. Okay, this is a main important lemma in graph theory and very, very basic. That could be taught in the first lecture of graph theory. Okay, so this lemma basically says that if you have n vertices in an undirected graph, again in an undirected graph, then the sum of degrees of vertices is basically 2 times the number of edges in a graph. This theorem holds because you can simply observe that if I have an edge E, and suppose this is vertex V, then this edge contributing 1 plus 1 to the degree of U and also plus 1 to the degree of V. So that means an edge corresponds to 2 degrees, right? 1 degree for 1 plus for degree of U and 1 plus for degree of V. So that's why the sum of the degree of vertices is basically twice the number of edges. Okay. So in base of this question, if I'll ask, suppose a graph, suppose G, every vertex has degree 4, then what is the number of edges?
2.
Sorry, I haven't given the number of vertices. Okay, suppose in a graph G, every vertex has degree 4 and there are suppose 5 vertices. Then what is the number of edges?
5 vertices and every vertex.
Just use the handshaking lemma. Okay, nothing else. I have 5 vertices, each vertex is degree 4, then what is the number of edges?
Well,
What? You can answer chat box.
10, ma'am.
Yeah, correct. Because basically what I have to do, I have 5 vertex v1, v2, v3, V4, V5, right? And each vertex has degree 4. So 4 plus 4 plus 4 plus 4. So it is simply 5 into 4. So 20. So that means 20 is equals to 2 into cardinality of E. So what is cardinality of E? Basically 10, right? So there are 10 number of edges if we have this type of situation. So these are the valid question which frequently asked. Okay.
Ma'am, you have written 6 vertices now.
Sorry, what?
Is it 6 or 5?
5.
Oh, 5. Sorry. Typo. 5. Fine. Yeah. So this is called the handshaking lemma. And okay. So now there is a theorem in which will count the number of edges in a tree. Okay. So if G is a tree with n vertices, then number of edges in G is n minus 1. This is a standard theorem. The proof of theorem is not that much difficult, but I am not covering it now. Just try to remember or understand. If you have an n vertex tree, so that means if you have if you have an acyclic connected graph which has n vertices, then it has n minus 1 edges. Okay, and this work vice versa also. That for suppose I mean, this statement could be you can think is that if G is an connected graph with n minus 1 vertices. Sorry. Connected graph with n minus 1 edges and n vertices. Then G is a tree. So that means G
Then
will
it is a
become
tree.
acyclic.
G
Sorry,
will
what?
become acyclic. Then G is a tree essentially.
Yeah, G is a tree essentially. I mean, the statement that it having n minus 1 edges plus connectedness will also imply it is tree. So that means there is no cycle. Okay. So, or this is a most important statement that if we have a tree with n vertices, then it precisely has n minus 1 edges. Okay. Right. So in BFS, DFS, our first target to be reachability, to solve the reachability question. And the second target of BFS, DFS is to find a minimum spanning tree. So what do you mean by minimum spanning tree? So minimum spanning tree, you can suppose like if you have a graph, suppose I have this graph. Suppose I have this type of graph. Suppose this is my graph with some vertices 1, 2, 3, 4, 5, 6, 7. Okay. Then what I mean by minimum spanning tree is basically a subgraph of this graph. Suppose something like that. Such that if now what happens, suppose this is the subgraph of this graph, right? This is G, this is H. I'm just leaving some edges from a graph in such a way that if I'll join any one of the edges, suppose I'll join this edge E1. So if I'll join this edge E1, so so this edge will form a cycle in this graph H. So if we have such type of subgraph, that type of subgraph is called minimum spanning tree. Basically, what you will do, you will take away those edges which are forming cycle in a graph G, right? And whatever you will remain, that is called the minimum spanning tree, right? You're getting what do you mean by minimum spanning tree, right? Is any doubt?
That's still a tree now. Means why minimum?
Yeah, it will still a tree because there is no cycle and it is connected.
Yeah, why we like, is there some another significance by writing minimum spanning? Or
Actually, minimum spanning tree is, actually it will span your whole graph. Now you just have to attach some edges, right? So that's the reason we have called it minimum spanning tree. Okay.
okay.
I think we are going from a graph to make it a tree.
Yeah,
What
to
is the
make it a
minimum
tree.
span, right?
Yeah. So that it
We
will
have a
almost cover whole graph, almost regardless some edges. That's
right. To
okay.
Ankit's point,
Yeah.
this is a tree, but
Yeah.
this tree is not given to us. This graph is given, and we have to
Yeah.
change that
Yeah.
graph into a tree.
Yeah. So that's the motto. That's what BFS and DFS do. BFS and DFS, that process will give us for any graph, we can get a spanning tree. Or more precisely, DFS won't always give a spanning tree, but BFS always give a spanning tree. You can forget about DFS. DFS won't give always a spanning tree, but BFS always give a spanning tree. For example, I'll
And
explain it. Yeah.
can you explain again? No spanning.
Yeah, minimum spanning tree is basically a tree which is, you can say that, which is hidden in a graph. So what you have to do, you have to pick away those edges which are forming the cycle in a graph. For example, here there is a cycle in a graph G. So if I'll remove this edge, I'll get a graph which contain one length cycle, right? Similarly, here there is an edge which is spanning a tree. Suppose this edge. So if I'll take away this edge, I'll get a graph which has again one less cycle, right? So what we'll do, so we will take away those edges which are forming a cycle and we'll convert our graph into a tree. That tree is called a minimum spanning tree, basically.
So we are removing only cycles, then it is an
Yeah. We just want to take all those edges which are forming a cycle, and at the end we'll end up at a connected graph which does not have any cycle. So that means at the end we'll end up at a tree. So that's why it is called a minimum spanning tree. Okay. Okay, fine. So the BFS process, what it does, so the BFS process will give us the minimum spanning tree of any graph. For example, if I have this type of graph, which we have discussed yesterday, something, some edges are connected like this, right? Or whatever it is. Okay, suppose this is my graph with vertices A, B, C, D, E, F. This is done, right? M, G, H. Okay, so if I'll apply BFS here, what does BFS trace? Okay, so suppose I'll start from which vertex? So suppose I'll start from vertex H. Okay, so what does BFS do? First I'll mark H, right? First I'll take H, then I explore its neighbors. Okay, so what are the neighbors of H? So there are three neighbors, G, I, and C. Okay, so there are three neighbors, basically G, I, and C. Then what does BFS do? BFS will reach out to each neighbor, reach out to each neighbor one by one, and then explore what are the associated vertices or what are the neighbors of that vertex. Okay, in this example, now I'll choose G. So what are the neighbors of G? So the neighbors of G, what are the unvisited neighbors of G? Be precise. Okay, so we won't consider I and H again. So the unvisited neighbors of G are simply C. So we will go to C. Now I'll come back to I, because in BFS we'll work level by level. So this is my level 0, right? This is my level 0. These three things are at level 1. So I'll come back to I, and then I'll explore what are the neighbors of I, what are the unvisited neighbors of I. But there are no unvisited neighbors of I, right? Because C has been visited by G, and G and H are already visited. So there is nothing new in I. So now I'll go to C and I explore what are the, okay, wait. C is again a neighbor of H. So this, yeah.
C is already
This is also not possible,
taken as,
right?
yes.
Yeah. So there are three neighbors of C now. Basically A, B, and F, right?
G4.
D also.
A, B, D, F.
Yeah, again, D is also a neighbor. So at C, I have 4 neighbors, 1, 2, 3, and 4. So these are at level 2. Right. Okay. Now I'll go to D and check out what are the unvisited neighbor of D. So simply E is the only unvisited neighbor of D. So I'll mark E. Then again I'll go to A, but all other vertices are already visited. So there is no unvisited. So observe here we get some type of tree, which related to our graph H, right? So I'll get this type of tree. This is my H. Then these are 3 edges going to G, I, and C. Then again from C, I have 4 things, that basically D, A, B, F, right? And from D, I have E, right? Okay. So this is the spanning tree of a graph of our graph G, this graph G. Okay. So in this way, we can find a spanning tree related to our graph G using the BFS process, right? You got, you guys are following, right? Is any
Yes,
doubt in
yes,
this
ma'am.
process? We just
No.
go to each, we just explore each neighbor one by one. We won't jump from level 1 to level 2 without exploring all the neighbors of that guy, right? For example, in H, I have 3 neighbors, G, I, C. So I'll explore G, I, C one by one. Okay. Then at C, I have 4 neighbors. I'll explore them one by one. In this case, I am getting I'm getting a neighbor in place of D, but that could happen that we cannot get a neighbor in place. I mean, if we have some other graph, we can end up with some other tree. That's why I'm done, right? Okay. So this is a concept that BFS does in terms of spanning.
Ma'am, is the same graph also called BFS tree?
Yeah, it's also called BFS string, but I think this terminology, okay, you can hear it in the lectures.
Ma'am,
Yeah.
why
Yeah.
would DFS not give us a spanning tree?
Actually, in DFS, what will happen? Let me explain. So I'll take same graph.
Mhm.
Maybe it will. Suppose we try to apply DFS in the same graph. What we get? Let's try. Okay. I also don't know. Okay. So I'll start from H. DFS, what we'll do? In DFS, I won't consider everything level by level. I'll choose any of the neighbor of H and go further till my path get end, right? Okay. So
Right.
suppose from H, I'll go to I. Okay.
Mhm.
Now again, there is a path from I to a new vertex, an unvisited vertex. Let us suppose I go to G. I can go to G, right? Because DFS does not do everything level by level. DFS
Right.
just move until the path will get in, right? Now from G, I will go to C because there is again a path. So I will go to C. Now from C, suppose I want to go to B. Okay. Now there is no path from B to any unvisited vertex, right?
Mhm.
Right.
Right.
Yeah.
So it will backtrack.
So I'll backtrack. So I'll backtrack till now. Till then,
To see.
to that vertex, so that I can get a path from a
Right.
new to a new
A
vertex,
new
right?
path. Right. Yeah.
Yeah.
So then you would go to C and then go to
This is D. Yeah. So
A.
I'll backtrack to C, but from C I have a way to go to D. Now from D
Okay.
again I have a way to go to E. From E again I have a way to go to F, right?
Mhm.
And from F I don't have a way to go to a new vertex because C is
Right.
already been visited, right? Okay, so now I'll again backtrack. So I'll backtrack to E. So again there is no another way. So I'll backtrack to D. There is no another way. So I'll backtrack to C. Now from C, this E, F, D, B vertices are visited. I and G also are visited. Simply A is not visited, right? So from
Mhm.
C, I'll go to A. So this is a tree this is a tree. Again, we get a tree, but it is not a minimum spanning tree. Why it is not a minimum spanning tree? For example, there is an edge between, what can I say? There is an edge between C and H, right? Yeah, but you will get a cycle if you connect this edge.
Right.
Forward edge. Yeah. C and I also have a edge. So again, we get a thing. But it should not be. I mean, it is not always the case. We get a minimum spanning tree. So maybe is then in this case we can get, or there is an edge. E to C we have, C to D we have, C to F. We can get a cycle. Yeah, again we can get a cycle, but this should not be the minimum spanning tree because minimum spanning tree is something look like this. Okay, so maybe in this case we are getting the minimum spanning tree, but it is not always the case that DFS will give you the minimum spanning tree. Okay.
Okay. Okay.
Does DFS guarantees a minimum spanning tree?
Yeah, BFS guarantees the minimum spanning tree because BFS work level by level. It won't
Okay,
jump out.
that's like saying that the height of the tree is minimum.
Yeah,
Is
I
this
mean,
something related?
Actually, in DFS, we are considered back edges, ma'am. Then it will get cycling.
yeah,
So,
yeah, that's the one kind of a thing that back edges will form a cycle, but the forward edges will not form a cycle. So I think those things may be more clearer in
No,
directed
but
graph.
but but if it for it, but the
But
purpose
if
of
we are in an
DFS and DF.
undirected graph, then forward edge and back edge both are same. So I think in an undirected graph, DFS also give a spanning tree, right? Okay, but basically you won't ask for giving a spanning tree because spanning tree are not always unique. You can get 2, 3, 5 or any number of, I mean not infinite, obviously there are some finite bound for the spanning trees, but there are possibility that different person will recover different type of spanning trees. Okay, so in general, what the question can be formed that you are giving a tree and then you have to observe a graph using the BFS process or DFS process. That the question can be asked in the reverse way, right?
Okay,
Then what
ma'am.
you have to do, you just have to apply BFS, DFS in the onto the options and recover a spanning tree from that and compare it to the given question. That's the approach you should apply.
Ma'am, but is the minimum spanning tree equal to the tree that has the minimum height
Actually, height also doesn't
level?
require to be same because here we have 1, 2, 3, and 4 levels, right? But
Yeah.
here we have 1, 2, 3, 4, 5. I mean, we have same other. I mean, this tree also can be drawn from upside down, or you can rotate into 90 degree, and the height will change. So those things we don't bother about. The main thing is that if you have a graph, you can apply BFS and DFS and require some tree from that graph, right?
No,
This much you
but ma'am,
understand.
if you go down,
Yeah.
then the path from C to D, E, F would increase the height of this tree, but it is still
Yeah,
a
yeah,
minimum.
yeah. Will still a minimum. So that's why we don't ask that compute the minimum spanning tree because minimum spanning tree is not unique. So there's no way you can find out the actual answer. I mean the common answer. So what we'll ask, we'll give you a tree and we'll say that this tree associated to which graph using the DFS or BFS process. That's the main question, right? So that means you should know the process for extracting a graph from using your method DFS or BFS. That's the main point. Okay, so you guys get how to extract a tree from the process, right? You got it?
Yes,
Yes.
ma'am.
Yes, sir.
Yeah, just try some questions in the practice assignment or in the activity questions. Maybe then it will be more familiar. Okay, now there is one other concept called DFS counting, so I'll explain it. Use the same graph. Okay. So suppose this is a graph and 0 to 1. Okay, let's go to 5 to 8, 9, Yes, okay. So DFS number. So what does DFS? DFS process will assign each vertex two numbers. First, suppose this is your vertex. So I'll assign it two numbers. First number is called pre numbers, and this one is called post number. Okay. So pre number will be assigned to that stage when we enter an vertex. Okay, or when we explore, when we want to explore that vertex, and post number will assign to that vertex when we leave out from that vertex. Okay. For example, in this graph, if I want to apply, if I want to use DFS, suppose I'll select my vertex 0. Okay, so I'll assign 0, the pre number 0. Okay, because I am starting from 0. Then from 0, I have two neighbors, 1 and 4. So the most common strategy is to take the neighbor which is lesser, I mean, in the increasing order will take. So from 0, I'll go to 1. It is not necessary, but it is the most common way to do it. Okay, so I'll go to 1. So when I go to 1, I enter 1 at the stage 1. So I'll assign it to be pre number 1. Then from 1, I don't have any other vertex to go, right? Any other new vertex to reach, right? So what I'll do, so I'll backtrack, so I'll finish the process to 1 of 1. So whenever you finish a vertex, you will assign that vertex that number, that post number. So we have done 0, 1, then I'll assign a number 2, then I'll go to 0. But 0 haven't finished it, right? From 0, we can move further. So I'll go to 4. So I'll went to 4 at the pre number 3. Then again 4, I have two stages, 4, 5, and 9 and 8. So suppose I'll go to 5. So at 5, I am entering at the pre number 4. But again 5. But again from 5, I don't have any new vertex to reach out. So I'll end my vertex 5 at the post number 5. Because whenever you end a vertex, you'll assign a post number to that vertex. Okay. So, but then I backtrack to 4. But from 4, I have again a new vertex 8. So I'll enter this vertex. So what is our numbering? 3, 4, 5. Now I'll enter at 6 to the vertex 8. Now again from 8, I have a new vertex 9, which can be reachable. So I'll go to vertex 9 with the pre number 7. Now from 9, I don't have any edge to any new vertex. So I'll end the process at 9. So I'll assign this vertex to be, since we are ending a process at 9, so that's why I'm assigning the post number to 9. I'll backtrack to the vertex 8. Now again from 8, I don't have any new edge or any edge which connect to the new vertex or which connect to unvisited vertex. So that means I have to stop my process at 8 also. So that means I have to assign a post number to 8 also. Okay. So I'll assign a post number 9 to 8. Then again, I'll backtrack to 4. Now again from 4, I don't have any any edge which is joining to a new vertex. So I'll again stop my process at 4. So I'll assign this vertex 4, my post number, basically 10. Then again, I'll go back to 0. Now from 0, I don't have any new vertex, right? So again, I have to stop my process at 0. So that's why I'm assigning the post number 11 to 0. Okay. So these pre number and post number, I'll call the DFS numbering. You got what I have done with this component, right?
Yes, ma'am.
We go to one vertex. If there is no other way for going to new vertex, we will stop that process. And whenever we stop our process, we will assign that vertex to a post number. Otherwise, we will move forward. Okay. So now you guys tell me what should we do with this component. Okay. So just either answer in a chat box rapidly, I mean, a little bit faster, or just speak aloud. Okay. So suppose I'll start with with 3. So the pre number will be 0, right? Now what should I do?
We have to do two sub edges, that is 2 and 7.
Yeah.
Uh,
So
Move
we'll almost choose the lesser one. So let's go to 2. So what is the pre-number at 2?
1.
1.
Yeah, 1. Just 1.
Then after 2, we can go to 6.
Yeah, just 1 second. Okay, Yeah, from 2 we have to go to which vertex? Am I audible?
8 to 6.
6 with pre-number
Pre number 2.
2. From 6,
6 to 7.
yeah, 7 with pre-number
Pre number
3,
3.
right? Now from 7
7 to 10.
with pre-number 4.
Pre number 4.
Now what happened when we reach at 10?
We are on a dead end, so we have to backtrack.
Yeah, we have to backtrack. So that means I have to assign a post number to 10. So the post number will be 5. Now I'm backtracking at 7, but from 7,
Then 11.
From 7 to 11
yeah,
branch.
we have 11. So we'll enter at 11 at pre-number
6.
6.
and again at
And
11
7
we have to
post.
stop
Post
here.
number
So we have
7.
to again backtrack and assign a post number 8. Then go to 6, assign a post number 9, go to 2, post number 10, go to 3, post number 11. Okay. So that's the call, assigning DFS numbering to a graph. And again, when we assign a DFS numbering, we simply get our tree also. Right? Okay. So this is called the DFS numbering. And what shall we do? So now the process is clear, right? How to assign numbering in any graph, DFS numbering in any graph.
We can start from any node, right? No, we can randomly.
Yeah, you can start from any node. The particular node will given to you that from which node you should start, because then only the question will make sense, right? Okay.
Ma'am, will there be any error if we will not go to the smallest number?
Sorry, what?
Ma'am, will there be any error in the graph if we will not go to smallest number after moving next?
No. There is no error. I mean, it is most convenience way that you are asking now that why are we taking the smallest number to move forward, right? That's your question, right?
Yes, ma'am.
Yeah, there is no error. I mean, it is more general way to do it so that we don't get confused or we don't miss out any vertex.
Okay, ma'am.
Now, what is remaining? Now we go to directed graph. As in directed graph, also we have to assign the numbering, but then we have to take care of whatever they called. I mean, in directed graph, you will proceed by the same thing, but then for moving from one vertex to another vertex, you will take care what is the direction of edge, right? Then only you will move forward, or then just try to backtrack the graph. Okay, for example, I'll just do it in this graph. Okay. Suppose this is my directed graph and I have to assign a DFS numbering to this graph. Then what I'll do, so let me start with 3. So I'll enter at 3 with 3 number 0. Then from 3, I don't have anything. So I'll again, so I'll end my process here also and enter it 1. Then I'll go to next vertex, which is, now I cannot go to next vertex. Okay. So that's this thing happen in the,
another. You have to start another
yeah,
one, right?
right. So here we are not even getting a tree, right? Right. So at 2, I'll start with pre-vertex, pre number 2, then move to vertex 6, let's suppose with pre number 3. Then from 6, I'll go to vertex 10 with pre number 4. Then I have to end the process here, backtrack 6. Nothing is there. So again, backtrack to 2. But
As
from 2, I have
like
7. Yeah,
ma'am,
sorry.
you're still using the term backtracking, but it
Yeah,
is just directed. So is
yeah,
it
but this is possible because there is no way going forward. So we have to backtrack it, right? I mean, there in backtracking, we are not using edges. We are just tracing our path backward.
okay? Okay.
Yeah, so you can do backtracking. Okay. So
We are
from
just using the stack in that case.
yeah, correct. The stack in that case. So from 7, I can go to 11 with pre number 8. Now I have to end the process here 9 with 10 and with 11. Right? I guess I'm right. So this is the case when
Ma'am,
you.
but from 7 there's a path to 3.
Oh, right. Again, there is a path to 3, so I don't have to end it. So go to 3 with pre number 10.
But
Leave
ma'am,
3 with post number 11.
three is visited, right?
He marked 3 years visited.
Oh, yeah, right. 3 has been
Yeah.
visited. Don't confuse me.
No, ma'am, but that's a different tree and this is a different tree, right?
No.
So
But
in
this
this
guy is visited already. When we start our process, we visit this vertex. If we suspend this vertex, we explore this vertex, and also we remove this vertex from our stack. So yeah.
yeah, but when you're starting a new tree, in that tree you have a path.
No. I mean, that's the thing, na. Here in the directed graph, DFS don't even giving a tree. I mean, it just give two different components. First component is this, and second component is this. I mean,
So,
DFS will
ma'am,
just telling that there is no way from going 3 to this component or this component to this component. That's
yeah. So with the directed graph, so we can find that many disconnected component, right?
yeah,
With help
that's
of
the thing.
DFS. Like for 11, we get another vertex. For 10, another.
Yeah, you can say that. I mean, in
But
this component, I mean, in this part, there is a way from moving one vertex to another vertex,
yeah,
right? But from 3, we cannot go to any other vertex. So you can observe these things in the questions
But ma'am,
also.
had I started with 2.
Yeah, so if you start with 2, you will get this component, but then you will also
Yeah,
get 3
no,
here.
yeah, but I will also get 3,
Yeah.
right?
So yeah, there's no uniqueness in this case also. But DFS numbering is important, so just keep in mind how to do the DFS numbering. Okay, you have watched the
ma'am,
videos of
one
DFS,
thing.
BFS.
So if we start to from so what is called? It is called like another DFS, or I mean same
Yeah. So
DFS.
this, the first DFS has starting point 3, right?
Yeah.
And the
So
second DFS has
it will
starting
end at
point,
3.
yeah.
Yeah, first DFS will end at. So the
Yeah.
numbering should start for
No,
2
no, no, no.
0.
First DF is not ending at 3. First DF is running from 3 to the last unvisited vertex. So that means, okay, let me explain. Okay, what is happening when I apply my DFS, which is starting from 3, I'm getting two components. First is this with this pre and post number, and second
Yeah.
one is this 2 and all, right? But what happen if I start my DFS from 2? I'll just get one component, one single component.
Yes.
That's the case. So the starting point of DFS somehow matters. Okay.
So
Now let's
for different component we
for
enumerated
different
with the
starting point,
series,
for
right?
different starting nodes, we get a different DFS tree or a different DFS. What can you say? Associated tree or associated components.
Okay.
Suppose I'll start with 11. Then what happens? Again 11 we
Then,
have same case, right?
yeah.
We cannot go to any other vertex. Suppose after 11 I'll choose 10 in my
Then again,
DFS process. Then again we have same problem, right?
Then if I choose 6, then also I will get only 1.
Yeah.
Yeah.
Another component, because 10 is already visited.
Correct. But you
Indirectly
know
it is.
how to give a DFS numbering to a graph given at a I mean, if someone give you a starting point, you can assign DFS numbering and you can extract a tree from using that node, right?
Yes.
That part is clear, right? Other
It
things you
just
can
became
explore in
clear.
the video lectures and questions also. Sorry, what?
It just became clear because when Ankit or somebody pointed that out, that 0, 1, we have to restart from 0, then it became
Yeah.
clear that no, we are actually, we have already consumed 0 and 1 here, and then we are starting from 2, not from 0
Yeah.
for the second component. Yeah. Okay. Thanks.
Right. So now next topic is topological sorting, or you can say dependency relation. So
Ma'am,
yeah,
where are these algorithms used?
these
In
algorithms
real
are
life or
actually,
in programming?
sorry, what?
Like in real life or in programming,
Yeah, in
where are
real
these
life
algorithms used?
you will see some of the examples where you can use it, because you again you have to do some other courses. I mean, the further courses for diploma or degree, whatever you are doing. In these courses, you have to use DFS for doing something. I mean, something related to data. Okay. First,
Ma'am,
what you will
networking.
do? First, we will convert our
Ma'am, you are
given
not
information
audible.
into graph or data, and then we will apply some of the process to reach out some conclusion. Okay. So I'm not taking those type of example now. I have to think.
Hello,
Yeah. Yes. You can tell.
ma'am, you are not clearly audible.
Okay. Now I'm audible. Hello.
Yeah,
Yes, ma'am. You're
Actually,
audible.
what I was saying that there are situations in data science, in data analytics, when you have to convert your problem into some graph, and then from that graph you have to extract some information. So for doing that, I mean, if the graph is so large, then you cannot do it by hand. You have to enter some code in your computer, right? So this DFS and BFS is a systematic way. You can decode it. I mean, you can code it into your program and get
yeah.
information using that program. So these types of question will take care by DFS and BFS. DFS BFS is such a basic concept in data science and algorithm, DSA, which you say.
Ma'am, Dijkstra algorithm is also using BFS in computers.
What? Sorry. So let me move forward, otherwise we will lose track. So now we go to DAG, which is basically the directed acyclic graph. Now you guys are familiar with the directed and acyclic word, okay? I don't have to explain it, okay? So in any DAG or in any directed acyclic graph, we can have a dependency relation. Dependency relation means that suppose uh, suppose we have a set of vertices 1, 2, 3, and so on up to n, and we say that our H set, or we can say simply that our tuple I comma j will belongs to E if and only if I appears before j, right? So dependency, I mean, you have given some relation. Regarding to that relation, if your I appears before j, then you say that we have an edge between I and j. For example, if I'll say that I have 4 courses, if I have 4 courses, maths, science, English, Hindi, geography, polity, sorry, geography, polity, and so what can I take here? Let's suppose some pure math course, algebra or calculus or trigonometry, right? Right, okay. And I'll say this is my level 1 course, this is my level 2 course, this is my level 3 course, level 4 course. I'll say that any person who want to do level 3 course, he should complete it all the courses which are appearing at level 2. So what I was saying that if you want to do geography, you have to complete these 3 subjects: science, English, and Hindi. Then only you can do geography. That's my constraint, or that's my relation. So using that relation, you can form a DAG, directed acyclic graph, in such a way that I'll take an edge between maths and science, because my relation says that maths appears before science. So that's why there is an edge between maths and science. There is an edge between maths and English. There is an edge between maths and Hindi, right? Because of my relation, I want to make a DAG, directed acyclic graph, regarding to my situation. So my situation is that I'm saying that a person can do a course if that a person can do a course of level 3 or level 4 if and only if he have done all the courses which are above, which are previous levels, or level 1 to 3, anything. Okay. So then there again an edge between maths and geography, because for doing geography, I have to complete it maths also, right? So again, there is an edge between maths and polity. And similar way, we can construct our whole graph. And you observe that the resulting graph will be a directed acyclic graph. So this is called the graph which is associated to some dependency relation. These type of relation is called dependency relation. Okay. So this is a situation where graph theory is used. Suppose you have some dependency relation. What you will do, you will convert that relation into a DAG, directed acyclic graph, and then you will work on it. That you can find an order. So you can find an order to complete your task. Okay. So here you don't have to, for example, if I'll say that I want to complete calculus. Okay. So what should be my path? Right. So first I have to complete maths. Then I have to complete science, English, and Hindi. Then I have to complete geography and polity after that. And then I have to go to calculus. So for completing calculus, I have an order that maths, science, English, Hindi, or these can be swapped, right? Regarding to my choices, if I want to do first science or first Hindi or first English, then I'll go to geography and polity, and then at the end I'll come back to calculus. So this could be my sequence for completing calculus, right? So such type of sequence is known as topological sorting. So that means topological sorting is basically that you have given a situation, you have given a DAG related to that situation, and for completing a certain task, you have to find a path, or you have to find a sequence for complete the task, is known as topological. This process is known as topological sorting. Okay. Any doubt in this thing?
Ma'am, can you explain how did you get this MSCH
Okay.
GPN?
So what happened? So in the above graph,
Mm-hmm.
my aim or my goal is to complete calculus.
Right.
Right?
Mm-hmm.
But my dependency relation says that if you want to complete calculus, you have to complete maths, science, English, Hindi, geography, and polity, right?
Mm-hmm.
So what
Okay.
happened? So suppose I want to, okay, fine. So for reaching calculus, I have to go through these many steps. But first I have to start with maths, because if I won't complete maths, I cannot complete science, English, or Hindi, right? So the
Right.
first task which I have to do is to complete maths, right?
Mm-hmm.
Now, at the level 2, I have science, English, and Hindi. So I can take any of the, I can take any of the sequence to complete this level so that I can move to the another level, right? So here I'll take science, English, and Hindi. So suppose I'll take English, Hindi, and science. So then I'll complete my level 2, right? So I want to reach at calculus. So that means I have to complete these things first, right?
Mm-hmm. Okay. Okay.
Yeah. So again, I have to complete geography or polity. So whatever order you want to take, you can take. And then I have to complete at calculus. So this sequence will give us a way to complete calculus regarding our dependency relation, right? So such type of
And this sequence is what we call topological sorting.
such type of sequence is called topological sorting.
Ma'am, for completing the calculus, the incoming
Yeah.
edges are from only G, P, and E. So after I go like after M, if I complete G, E,
No,
P, then
sorry. Here, all edges are connected. I haven't drawn.
okay.
I thought, yeah.
Ma'am, and it's
That's my
also quite
condition, that
possible.
if
Okay.
I want to enter a course which is at other level, one level before, one level ahead, then I have to complete all the courses which are at the present level.
Yeah.
That's
Ma'am, it's
my,
also quite possible that this sequence is also not unique because a lot of like
yeah, this is not unique. Obviously, this is not unique, but there exists a sequence or there exists a path. I mean, there exists a topological sorting.
yeah.
Obviously, topological sorting is not unique because you can permute these three things, right? You can permute geography and polity also.
Yeah.
This is
So
a
for
one topological sorting. Yeah.
every DAG there exists a topological
Yeah,
sort.
yeah, yeah. For every DAG, there is just a topological sorting. That's the main. That's the next theorem we have to do. Okay. So that one thing, and how to do a topological sorting in any general graph. That's the other thing. So just let me take example. Okay. So there is a lemma or theorem that says in every DAG, because DAG is directed, right? Directed acyclic graph. So there exists an vertex with in degree 0. This is a first remark which will ensure us that okay, you can apply topological sorting type. Okay, so this is a theorem. So I'll explain with the example, but first understand it. So if you have any DAG, then there always exists an vertex which has in degree 0. Okay, so let me just explain a proof in a minute. Okay, suppose there does not exist any vertex, and suppose I in my G, my vertex set is basically v1, v2, and so on, vn, right? Okay. So what can I do? So I'll take a vertex. Suppose I'll take v1. And I am assuming that there is no vertex within degree 0. So that means there is a vertex which is going at v1, right? Because v1 has in degree 0. So there is an edge which is coming at v1, right? So suppose this is my v3. And suppose I have 8 vertices here. Again from v3, since v3 has in degree at least 1, so there exists some vertex which again related to v3 preceding, which is going to v3. You can somehow say, suppose this is v4. Again, since v4 has in degree at least 1, there is again a vertex. So at the end, you will reach a vertex. Suppose from v6, there is v7 is related, v5 is related, and at the end v8 is related. But again, I am saying that v8 has in degree 0. So that means there is an vertex which is related to v8. It need not be the case that v1, but any of them. So let us assume that v4 is related to v1. So in this case, what we get? We get a cyclic. But this is not possible in DAG because DAG is basically acyclic, right? So this will give us a contradiction. So the basic idea of proof is that you can backtrack each vertex. Since we have in degree at least 1, so we always get a distinct vertex which is going to that vertex. And at the end, we end up with a cycle. So that's why in every DAG, there should exist a vertex which has in degree 0. Okay, clear?
Yes, sir.
Yeah. Everyone, right?
No, ma'am.
Not clear?
Yes, not clear.
Oh, okay, fine. Let us suppose Suppose this is your DAG, V1, V2, V3, V4, V5, V6. Okay. So this is your DAG. No, this could not be your DAG. Okay. So the ultimate idea of the proof is that you can backtrack, right? And we have finitely many vertices. So at this at the end stage, you will get a sequence which will which will exhaust all the vertices from V1 to Vn. And at the end, we get a vertex which is at least one of them. So then we'll form a cycle. So something like that you can say. Suppose I'll start with this vertex. I'll go to some another vertex, go to some another vertex, again go to some another vertex, another vertex. Suppose at the end I'll finish my whole vertices using the path. But now this vertex is also connected to any one of them because I'm saying that in degree is not zero. I'm assuming that in degree is strictly greater than zero. So that means in degree could be one. So that means this vertex has a vertex which is related to it. So in that situation, we can get a cycle. That's the main idea of the proof, basically. Now you are understood, or should I do something else? Yeah, you can say, if it is not clear, then you can easily tell.
Starting one should be no incoming. That's something.
Starting vertex could be anything. For example, I'm taking this is for example. I think at the end, what happened? Okay, let us suppose in this way that suppose you live in a town, and you say that that in that town every road is connected to every other road, right? So you start from a house and you backtrack all the houses. That you start from your house, go to your neighbor house, go to that neighbor house, again go to that neighbor house, and just do this thing repeatedly. What happened at the end? At the end, you will reach to your whatever your starting point, or at least one of the what can you say? One of the houses which are already has been visited, right?
Yes.
You get this scenario, right?
Yes.
So that means at the end you get a simple cycle. But in a directed acyclic graph, cycles cannot happen. So that's why there is some stage, there is some road which from which you cannot move backward. So you can relate.
Ma'am,
Yeah.
ma'am, DAG has to be a tree then.
Directed acyclic need not to be connected. That's it. Directed acyclic need not to be connected, right? Tree is always connected.
Cyclic means no cycles now. That's it.
No
Sorry,
cycle,
what?
but there can be disconnection. Okay.
Yeah, there can be disconnection. Sorry, sir? I haven't heard. Okay, fine. So now I'll explain how how can you get topological sorting. Okay. So suppose I have a graph. Don't have a graph. This is my graph. Suppose this is my DAG 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Right? This is a DAG because there is no cycle. For example, here I can go to, I can move from 2 to 3, 3 to 4, but I cannot move from 4 to 5 to complete my cycle, or from 5 to 2 to complete my cycle, right? Similar situation is happening here, that I can move from 5 to 7, but I cannot go back from 7 to 6, because the direction says that you can only move from 6 to 7. So this is your directed acyclic graph. Okay, now you have to give a topological sorting, okay, any topological sorting. Sometimes you have given a vertex, otherwise you just have to do any topological starting at any vertex. Okay, so topological sorting started with a vertex which has in degree 0, right? So first step is find a vertex which has in degree 0. Since we know that in a DAG there always exists a vertex, right, which has in degree 0. So you can find a vertex which has in degree 0. So what is that vertex in this graph which has in degree 0?
Ma'am, 1 and
1.
6.
1, ma'am.
Yeah,
Six
correct.
also.
1 and 6 also has in degree 0, correct, because it has out degree 2, right? So you guys get right, because degree of 1 is 0, because there is no edge which is coming to 1, right? Okay, so let's start with 1 or 6. What do you want? We can start with any of them. So let's start with 1. Okay, so when we select our first vertex 1, what we will do, we will erase that vertex, and we will, okay, before starting topological sorting, it is always better to mark all the in degrees of all the vertices. Okay, so I'm marking in degrees of all the vertices. So this vertex has in degree 0. Here I have in degree 1, right? So this vertex has in degree 2, because there are 2 edges coming at 3. This vertex has in degree 1, because there is 1 edge coming to this vertex. Again, this 10 has in degree 1. This 8 has in degree 1. 11 has in degree 1, 7 has in degree 2, 6 has in degree 0, 5 has in degree 2, and 4 has in degree 2, right? So these are the in degrees, right? Am I right or not? Yeah. Yes.
Right.
So start at 1. What we will do in next step, we will erase our vertex 1, and we will also erase the degree of those vertex which is which the edge connected to 1 contributed to other vertices. In this case 1 is connected to 2, so if I'll remove 1 and the edge associated to 1, then the in degree of 2 will become 0, right? That means if I remove 1 and also associated edge, now the in degree of 1 will become in degree of 2 will become 0. That's the point, right? Correct? This is your second step for getting any topological sorting. So remove the vertex X and edge associated to that, and also correct the in degrees, remaining vertices in degrees. So when we remove 1 and the associated edge to that, then the only in degree which should be corrected is the in degree of 2. Now 2 is a vertex which has in degree 0, and 6 is a vertex which has in degree 0. Now this will become our new DAG, right? So our old DAG was this. Then from the first step, I am removing this vertex and the edge. So I'll get a new DAG which has the new in degrees, right? So now I'll repeat my process, that again I'll select a vertex which has in degree 0, and again I'll do the same thing. Okay, so which vertex should I select now?
6.
Okay, let's select 6. So this is my second selected vertex, 6. Okay, so in the third step, what I'll do, so I'll remove 6, I also remove the associated edges to it. So I'll remove 6 associated edges also, and also correct the in degrees of those vertices which are affected, right? For example, now 5 has in degree 1 and 7 also has in degree 1, right? So third step has been done. Now moving to fourth step. Now again, fourth step, I have to select a vertex which has in degree 0. Which vertex should I select now?
2.
2, right? Because 2 is the only vertex which has in
Yeah.
degree 0. So I'll select 2. And in the next step, I'll remove 2 and also remove the associated edges to 2 and correct the in degrees. So remove 2, remove the associated edges and correct the in degrees. So now the in degree of 3 will become 1 and the in degree of 5 will become 0. Now observe at every stage we are getting a vertex which has in degree 0. Okay. So in the fifth step has been complete. Now at the sixth step, let's suppose which vertex should I consider now? 5, right?
5, yes.
Yeah, 5. Now again, just remove 5. Remove the vertices also. Now this will become disconnected, but we don't bother about that. Okay. So now 7 has in degree 0. Okay. Now again, I have missed here that this 3 also has in degree 0. Okay. So now sixth step was also done. Seventh step. Okay. Okay, seventh step was removing 5 and its edges and correcting the in degrees. At the eighth step, which vertex should I consider now? I have two vertex of in degree 0, 3 and 7. You can consider any of them. So which should I
7.
select? 7.
7.
Okay, fine. So if I'll select 7, and in the next step, I'll remove the edges or vertex 7. So if I'll remove 7, there is no correction on in the in degree. So now at the next step, I have to select the vertex 3, right? Because 3 is the only vertex which has in degree 0. And again, I have to remove 3 and the associated edges also. So here the in edge and the out edge, both edges will cancel out. Okay. So now here I'll getting a new DAG in which the in degree of 9 is 0, in degree of 4 is 0. So at the next step, I'll select 9 or 4 anything. So suppose I'll select 9. Then I'll remove 9 in associated edges. Then I'll select 4. Again, I remove 4 and associated edges. Now here also the edge, the in degree of 8 will be 0 because there is no edge connecting to it. So again, I select 8. Again, I remove it. Now you can select any of them. This has 0, this has 0. So I will select 10 and I will select it. So what is the main sequence I have got? First started with 1, then 1, then 6 to 5. So 1, 6 to 5. And then 7, 3. 7, 3. Then after 3, I guess I'll go to 9, 4, 8, 10, 11. This is a one topological sorting for given graph. This is a process for constructing a topological sorting in any DAG. You guys understood? It's easy. Just take a vertex which has in degree 0, and in the next step, remove that vertex and also remove the edges associated to that vertex. You'll get a new DAG. In that DAG, just correct the in degrees. Again, you get a vertex which has in degree 0. Again, select it, remove the edges, and you can form your topological sorting easily. What happened?
Ma'am, they will give graph and ask us what is the shorted
Yeah.
list property.
Yeah, they will give a graph. They will also give a topological sorting to you or give a sequence to you and ask that this sequence is possible or not. Because there is no unique topological sorting. Because in some stages we get two vertices which has in degree 0. So you can choose any of them. So that's.
They will give shorted list. Then first one is the 0 incoming.
You started with a vertex which has in degree 0.
That one. First one is the in degree 0.
Yeah, in degree 0 vertices.
Thanks.
You can this process is clear to everyone, or there is some doubt, you can ask. You can ask in Hindi also, that's no problem. Okay, because this is important. You should able to find out topological sorting, or you should know that this topological sorting can be happen or not. The process is easy, but it's important. Should I try one other example? One more example of topological sorting?
Yes.
Ma'am, can we get this DAG which
Yeah.
we have sorted in topological order?
Yeah.
Because I have one question about that. Like
Yeah.
with this DAG we have the vertex 2
Hmm.
having in degree 1.
Yeah.
So
Actually, we
if
have
we
removed the grad tag. So
that's what the problem is.
it is not possible to get the tag.
Yes.
Yeah. So
Okay, then
I'll do
let
another
me-
example.
Yeah,
That
please.
I'll do the same example which I have done in the video lectures. Okay, because I don't have any other tag. 2, 3, 4, and there is an edge between 1 and 2. Then 3, I have 5, 7, 6. Okay. Now you guys answer what are the in degrees of all the members. Okay. So what is the in degree of 1?
0.
You can answer in the chat box also. 0, right? What is the in degree of 0?
0.
0.
Yeah. For 2?
2.
2.
For 3?
1.
1.
4, 1. 5, 2. 6, 1, 7, 2. 7, 3.
4.
7.
4.
Oh, 4. Yeah, 4.
7, 4, right? So start with the first step. So I have to select a vertex. So which vertex should I select?
0.
Let's select 0. Now in the second step, I have to remove the edges associated to 0. Yeah.
Ma'am, can we select one also?
Yeah, you can select 1 also. That's why I'm saying that topological sorting is not unique. You can select 0 or 1, any of them. So okay. So let's try with 0. It's also easy. Okay. So now I will remove 0 from my graph, from my DAG. Okay. And then I will update the in degrees which are affected because of this removing or because of this erasing. Okay. So now suppose this is your new tag. Now answer what are the in degrees of all vertex. What is the in degree of 1?
1 remains unaffected. 2
Yeah, what is the in
becomes
degree
1.
of 2?
3 and 4 becomes 0.
3 will become 0, 4 will become 0. Everyone is clear with this situation, right? What are we doing? Any doubt regarding this step?
No,
No?
ma'am.
Yeah. We just correct. So we just erase the edges associated to 0 and update the in degrees. Now in the second step, which vertex should I select? The only possible choices is 1. Okay. So I'll select 1. I'll remove the
No, ma'am.
edges.
3 is also an option and 4 is also an option.
Oh, yeah. So this is 0. Yeah. So which vertex you want to select?
It doesn't matter, ma'am. I was just pointing that.
Yeah. So let's select 1 itself. It doesn't matter. So after selecting 1, the in degree of 2 will become also 0. And all other degrees will remain same, right?
No, ma'am. 7 becomes,
7
I
become
think, 3.
3. Yeah. So that's the thing. You have to update all the vertices, all the degrees of vertices which are affected because of that removing or erasing. Okay. Now let me select 2. Then I'll remove 2, and the degree of 5 will become now 1. Right? And no other changes. Correct? Now let me select 3 and remove 3 and update the degrees. So now the degree of 5 will become 0 and the degree of 7 will become
2.
2. Right? Okay. Now now let me select 4 and now I remove 4. I also update the degrees. This will become 1. Now the thing are same. Select 5, remove it, again remove it. So this will become 0. Now I'll select 6 and at the end again I'll remove the whole things. So at the end what I'll get? So I'll get simply 7. So this is 7. So this is your required topological sorting. Now it is clear, right? It is clear or not?
Yeah, it's clear.
Yes, ma'am.
Fine. So till this much you guys should understand. There are some topics regarding the complexity of adjacency matrices and adjacency list. Just go through that lecture. It's not that much tough. I mean, it's just informative. You don't have to prove or you don't have to understand anything. It's, I think it's lecture 8 or 7 something.
Yeah, ma'am. I have posted the question in the chat box. Please refer that.
You have doubt?
Yes, ma'am.
Yeah. What is your doubt?
Yeah, ma'am. Well, that one, the topological sorting. The graph I have.
Okay, you want a topological sorting for this graph.
Yes, yes.
Okay. So now you can do, right? I mean, fine. So
Yes, ma'am. But after 2 steps.
Yeah. After 2 steps, you are not getting. Okay, so let's just
Yeah.
discuss this last example. Okay. So this is your graph. Now it's gone. Wait.
Yeah. This graph is the first example you have discussed, but I only make the changes. You have given that the one is from 2 to 5, but I have made that both ended.
Okay,
Like,
okay.
undirected.
This is your graph, right?
Yes.
So let's assign the degree for each vertex. So this has degree 0. This has degree 1. Again 1. For 3 I have 1. I guess for 5 I have 1. No, but for 2 I have 2, right?
Ma'am, first of all, is it acyclic or?
Yeah, that's
Because
the thing. This is not DAG. I mean, we can do topological sorting in a DAG only.
yeah, but
Yeah,
how it is not DAG?
because there is a cycle, right? Yeah, I thought it was. You can just start from 2, move to
Yeah.
3, move to 4,
No, ma'am, there's no cycle.
but no, there is no cycle.
Yeah,
You cannot go back.
that's what.
And
So it is a
this
DAG,
cycle
right?
we won't have. This is also we won't have. Yeah, this is a DAG, so we can topo. So the reason is that why we want. Yes, sorry. Yes, you can say. Okay, fine. So the reason why we want a DAG, because if we don't consider a DAG, there will be a situation, there will be a stage in which you won't get any vertex which has degree 0. So that's why we always want to consider a DAG. So I think this is a DAG. So let's try the topological sorting. So 0, the degree is 2. Now the
It
degree
will
is
not
1.
work, ma'am. After 2, that is 1 and 6 are removed, 2 will have 1. So everyone would
that's
have
what I
at
got.
least 1.
No.
Yeah.
But then 7 will become the 0 now.
Okay, 7 becomes.
Okay.
Yeah.
So what is the
Yeah,
in degree of
okay.
5? It is 2. Let's try now. If not, then we'll get something new. So
Ma'am, for 3 it is 2, right?
for 3, it is 2. Yeah,
3.
this is a two-sided
Yeah,
edge. Yeah. So let's just work with these numbers only. So the first member will be 1. So if I remove 1, remove the edge, the degree of 2 will become what now? 1.
one.
And all other things will be as it is, right?
Yeah.
I'll select 6. So if I remove 6, the degree of 7 will become 1. Okay, now the 7 we don't have, right?
Yeah.
But we should have. Either this is not a DAG, because that's the thing now, because whenever we remove a vertex from a DAG,
Yeah, actually.
then the
Yeah, we have
remaining
the
graph will
theorem.
be a DAG.
Yeah.
If it is the case, then there is a catch. This has in degree 1. This again has in degree 1.
Yeah, I think the
In degree 1, this is in degree 2.
we have this undirected edge. That's what the problem is.
We have
Because
what?
for yeah,
Okay, wait.
undirected edge,
Yeah.
because
Now I got it.
for an undirected
Yeah.
edge, we don't talk about the in degree or out degree.
Yeah. This is not an indirect. I mean, what you are saying?
Yeah, I'm saying that for an undirected edge, we don't talk about the in degree or out degree.
But there is no undirected edge. Every edge is directed, right?
Yeah, both directed. That's what.
Yeah, both directed. So we don't talk. No, we talk about in degree. What happened now? There is one other thing about topological sorting.
Yeah, okay.
That for topological sorting, we want dependency relation. We want dependency relation. Dependency relation means that either I should happen before J, or J should happen before I.
Yeah.
Right? Okay. So again, in a DAG, we don't have this type of edges, because if we have this type of edges, what does this edge means? This edge will
Both
imply
are
that okay,
dependent to each
first
other.
first I should have first the event I will happen and then J will happen. But the same edge will saying that okay, first event J will happen, then I will happen. Then what happen? Both of the person I and J will wait for each other, that okay, first you will start, and he will say that first you will start. So this type of situation does not happen in a DAG. So it is not a DAG because it has a two-sided edge. Okay. So a two-sided edge eventually forming a cycle. This is I and this is J. So you can say it is eventually forming a cycle, but the dependency relation tell you that this should not happen. Because suppose I'll say you that you should complete maths 1 before stat 1, and the other day I will tell you you should complete stats 1 before math 1. So that means you cannot do both of the courses, right?
Yeah.
Suppose I will tell you that you should do stats 1 before math 1, and Arpit will tell you, okay, first you will do math 1 before stat 1. So then you cannot do any of the courses, right? So such thing won't happen in a dependency relation. So that's why this is considerably, it is a DAG, but it should not contain such two-sided edges, because then two-sided edges will contradict our dependency relation. That's a good example. Thank you.
Okay.
Ma'am,
Yeah.
While we are doing this sorting,
Yeah.
so two edges are coming in 0, then which one we have to take first? Because they're asking a sorting list afterwards.
Sorry, I'm not getting your question.
No, ma'am. If after once we started,
Yeah.
so we'll get two edges that in degree is 0. Then which one we have to take first?
You can take anything, anyone. That will be a topological sorting. There is no harm of taking a in the previous example.
Sorted list will come differently now.
No. That won't happen. I mean, question won't ask. A person won't ask you to give a topological sorting, because he knows that the topological sorting is not unique. What he will do, he'll give you a topological sequence, sorting sequence, and then ask you that it is a valid topological sorting sequence or not. Okay. Yeah. That will be the valid question. Okay, so this is a nice, you can say nice situation in a dependency relation. That because we know in dependency relation cycle will not happen. I, J, K, and again go back to I.
Yeah.
Because
So
this will happen, then everyone will wait for other to complete their task.
yeah.
We cannot do
So
anything.
yeah. So
Yeah.
one more question. So what is this graph called? Like, is it DAG or not, or is it cyclic or not?
Actually,
Like,
it should not be
sure, it
cyclic.
is. Yeah.
It is
Yeah.
cyclic.
Cyclic.
Yeah, I think it should not be cyclic, or
Yeah.
because in a
It is
directed graph,
acyclic, but
yeah, in a directed graph, we can have such type of edges. Then ultimately, this edge is telling you that you can move in both direction. So you just go from 3 to 8 and then go from 8 to 3. But in a cycle definition also contradict, because cycle is a path which has starting and end point is same. If I consider this to be cycle, then I'm going from 3 to 8 and 8 to 3. Yeah, so this is a cycle, right? So it is not a tag. Convince?
no, ma'am. because
Yes, ma'am, we
we
can say
we
that
are not
because
Yeah, we
getting
can say
starting
that
and
cycle.
now,
ending
because
points are
what
same.
we have 8 and 3 here, and we have two-sided edge here. This is similar
Yeah.
situation that we
Okay.
have 8 and 3 here. We have an edge coming, which is reaching at 3 from 8, and again 3 to 8.
Oh, okay. Okay.
Ma'am,
This will give us
even
that
if it
8,
is,
3, 8. Sorry, what?
ma'am,
Oh,
Yeah.
ma'am, even if it is like unidirectional, then
Huh?
also we cannot get at the point at 7, like 0 degree at 7, nama.
Then this edge won't happen, right? Because this is also two-sided edge. So
Yeah.
such type of
Okay,
edges
okay.
also won't happen. This is also won't happen. So in that case, we get a 0 degree, I guess. Either this will be this direction or that direction. Because if you consider one of the direction, if you remove, yeah, because if you consider this direction, and if you remove one, then if you remove 6, then also we have a problem, right? But then again, we have to consider this edge. I mean, if you consider this direction, then there should be a cycle. Okay.
if we
Ma'am,
consider
we
from
can
only direction from 5 to 2, then 5 would be the 0 in degree.
Yeah, correct. Then
After
5 will
6.
be the next vertex which we should select it.
Yeah, then we can proceed.
Right.
Yeah, ma'am. So simply we can say DAG should not have any undirected edge, right? Because
This
it
edge you
violates
won't
the
consider
cycle,
as undirected,
acyclic.
but yeah, not two. I mean, what you can say, two direction edge, or yeah, undirected edge will do. It is not
Because
be precise, but yeah, fine.
yeah.
Nice. Any other doubt? Yeah, we should discuss such type of question, because then only it will become clear. I haven't come across this question, this graph. Yeah, you guys have any doubt? Now it is clear. What do you mean by topological sorting and all?
Yes, sir.
Yeah, fine, nice. So, shall we end this session here, or you guys have any doubt regarding any situation? Anyone?
Yes, ma'am. One doubt.
Yeah.
10.6. Activity 10.6.
Activity 10.6.
Actually, a lot of doubt. But
Yes, wait.
yeah, two questions. Question number
Question
2 and
number?
3. Yeah.
3.
Second and third, yeah.
Yeah, just 1 minute. Okay, in the second question, there is a forward edge and backward edge. No, which of the following cannot be an edge in the original graph? Okay, so such type of question. Does everyone tried this type of question? Activity 6 of second. No. So basically, let's suppose there is an edge between E and F, right? The answer is E and F, right?
Yes, yes.
So if in a graph, if you suppose there is an edge between E and F, then you won't end your DFS at a node E, because when we end our DFS at any vertex, if there is no other unvisited vertex, right? But if there is an edge between, you can go further from E to the unvisited vertex F. So that's why this edge cannot be in a graph. So you can think about, the hint is here that you will end your DFS if there is no edge or there is no unvisited vertex which can be reachable by an edge from the last vertex. Okay, then only you can end your DFS. So just think using this fact. We'll discuss in the other solve with us next session. Okay, it's a nice question.
Okay.
So I'm giving you hint. Just try to understand when will your DFS will work,
Okay.
or when will your DFS will end at a vertex. What is the condition when we say that? Okay, when we backtrack, when we want to backtrack, we make sure that there should not be any unvisited vertex which can be reachable from the given vertex. Okay.
Yeah.
That's it.
And ma'am, for BFS,
For
because
BFS,
question number 3 about, yeah.
Okay, for BFS, I think you should consider it to be a neighbor. Similar way, question number 3, right? Okay. For
Yeah,
BFS, it is much more easier, because if there is an edge between these two vertices, then that will be a neighbor, right? So that neighbor will be treated in the next level, because you observe the graph is given by level. First level is A, second level is BC, the third level is ED, and the last level is FNG. So consider there is an edge between A and E, then the E will appear in a level 2. So that means here you have to think about at which level, if there is a edge between these two vertices, at which level this vertex will move. For example, if there is an edge between A and E, so that means E is a neighbor of E, right?
yeah, right.
Right.
Oh,
so the E
so
will appear in a level 2.
Yeah,
It should not be in the
okay.
level 3, right? I mean, sorry,
Yes,
0, 1,
yes,
2. So if we start with 0, 1, 2, it should be in level 1, not in level 2.
yeah. It
So
should
this is
be
a,
level, the same level, or the at least
yeah,
next level, not
huh.
beyond that.
So I mean, I'm giving you just hint because others should try.
Yeah, okay.
Okay. So yeah, Abdul asked some question. Is this in a factory? There are performed a different requirement in a factory. Oh, this is a question related to present a minimum. Okay. So this is a question related to vertex cover or something, I guess. I have. Yeah. Point such an any employee can reach a single point without going to pass. You just try to draw a path between. What can I say? I mean, just understand question. It's easy. Abdul, you have sent this. Am I
Sorry,
audible?
ma'am. What I'm not able to understand is why are there slashes here? What does this slash means?
Oh, this is a typo. Actually,
Oh,
this slash means the bracket, the second bracket. Just a typo, okay?
okay. I was confused with those slashes. I didn't have the doubt
Yeah.
about.
Yeah, just a typo.
Okay, thanks.
Okay, so I'll share the PDF and then I think we should end the session here.
Thank you.
So I have shared the PDF. If you guys don't have any doubt, you can leave. I will also end the session within 10 minutes.